So when we're looking at an action potential, I often draw a neuron. And a neuron, and by the way, just as we're talking about this, to remind you that the neurosurgeons are coming again today. So this is usually what's drawn when you're talking about action potentials. It's a cell. It has mitochondria. It has vesicles. It has all the stuff that cells have. And if you did the ecstasy case study, you know that there's vesicles all the way down here at the terminal end of the axon that is where at the synaptic gap where you're going to get vesicles of neurotransmitters fusing to the membrane and doing exocytosis over here. We'll look at that before too long. But along this membrane, we talked about there being this myelin sheath. So there's this fat called myelin that protects. What this does is it makes it faster. Instead of having this entire length, remember this cell can be very long. So if you had a very long distance to make a signal happen, it would take a longer time than is physically possible. By the way, it goes all the way across here. I'm drawing it like it's cut open, but it would go all the way across. But imagine I cut this open, so you're only looking at a half of the. And I'm making these gaps big because I want to be able to draw in them. But this thing here is called the node of Ranvier. And the node of Ranvier is where these ion channels exist. The myelin sheath, bless you, makes it so that the only place you're going to get a change in the chemical concentration is here. So when you have two magnets, do the magnets have to be touching for there to be a force field? No, they can just come close. And so when we change the ion flow across this membrane, it creates an electrical potential change that triggers the next node. So when you get the voltage-gated channels opening here, they open here, 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 all the way down. So you have like an arc, if you can imagine an arc. You know, like you static electricity, like a lightning bolt. All right, so you can imagine a small lightning bolt. It's not a lightning bolt, but imagine a little lightning bolt here going from one space to the next space to the next space. So now the signal can jump down the axon. So when that way there's a lot less travel time between the beginning of the signal and the end of the signal. These myelin sheaths allow you to think quickly and to react quickly. Without them, this signaling mechanism would not work. There is a disease called muscular sclerosis, but it's also another one called MS, multiple sclerosis. And what that is a disease where your body attacks the myelin and destroys the myelin, effectively making the neuron dysfunctional. So it starts with usually the peripheral nerves like your vision or your motor neurons, and you start to shake and you can't really move. You go blind or have double vision in an eye. It can get really bad. It got really bad for my brother when he had it, and his neurons started to become dysfunctional. The symptoms can be very, very severe, but the reason that it's happening is that the myelin sheath is being destroyed. And so this signal can't jump. It has to open all the channels all the way down. It takes too long, and what you get is this dysfunction, right? This disease. Yes. Double vision. So you have, instead of seeing one of me, you'll see two of me, right? So it's because one eye is not synced with the other eye. Your neurons are firing too slowly, and they get to the point where neurons start to die, and that's really not a great place to be. All right. So there's some channels here that we should look at. Let's go ahead and let's go. I was gonna zoom in and look at it, but you know what? What might make more sense is if I just do one of these things, if you don't mind, I will do a close-up of what the node of Ramvé would look like. Is that okay?
Sure.
Sometimes people get confused. If you're confused, now's the time. Don't tell me it's a different language tomorrow when I'm telling you now. So you have these channels. There's 3 different channels. Right now we're going to look at maintaining what's called the resting potential without a signal going off. What the axon would look like when it's at rest. There's a potassium channel, and we call it a leaky potassium channel. Potassium ion channel. Now, I guess the first question that you have to ask yourself is, where is potassium higher? Inside. That is correct. So potassium ion is higher inside. Where is sodium ion higher? Outside. Sodium ion is higher outside. So that's the first thing you have to know when you're talking about a membrane potential. On an overall picture, you have to think about the fact that there's 2 gradients. Remember what a gradient is. Who remembers what a gradient is? It's when you go from high to low. From high to low, right? So there's 2 gradients. There's a gradient. Remember we talked about gradients being the thing that we do in art where you do shading. You go darkest to lightest. You remember discussing that?
Yeah.
Well, there's 2 gradients we're talking about here. One's a chemical gradient. The other's electrical. That was your bell work question today. The chemical gradient is dealing with the concentration of sodium ion, mostly. There's calcium, but let's go ahead, sodium, and potassium. And yes, we'll have to add calcium to it as well. There's calcium is a +2, by the way. So those 3 ions are the major ions you get. There's chlorine as well and all these others, but let's worry about that. And the electrical gradient is where it goes from very positive to less positive. So these are 2 gradients. So you get very positive to less positive, very high concentration of sodium, very low. So over here on this inside, of course, I hope you know that this is inside and this is outside. The outside is very positive. So that's the electrical gradient, and the inside is very negative, less positive. In fact, one way we measure the difference between sides is measured in volts. So we talked about that with batteries, and we talked about that with all kinds of different examples, but we measure in volts. In this case, the inside is negative 70 millivolts at rest. So that means the electrical gradient is more positive outside, 70 times more positive outside than it is inside. That's all the negative means. How do you maintain that? Because what causes it to be negative 70 is that there's more positives outside than there is inside, correct? Positive what? Ions. The chemical gradient is what creates the electrical gradient. So we have leaky potassium channels, which means potassium is going to go in which directions? If it's a channel, it's not active, it's passive. So in which direction is potassium flowing? Through the leaky channels. It's going out. Oops, I hate drawing it that way. It's going out, right, through these leaky channels. So here's a question for you that's going to go directly to your test, your practice test. Are the leaky potassium channels, are they depolarizing? Are they inducing a depolarization or making depolarization more difficult? Why is it making it more difficult? Why is it inhibitory postsynaptic potential? Why is the leaky potassium channel an example of an IPEP? Why is it making IPEP more, the movement of this increasing the inhibiting the action potential? Because what is it doing to the membrane?
Is it because like it be going out but then coming back in on the other one?
No, that's a good point. We're going to talk about that in a minute. But it's going out. What's it doing to the action to the polarity of this membrane? It's making more negative or more positive, more polar or less polar.
More positive, sorry.
Making what side more positive?
The outside.
The outside more positive, so that means the inside is what? More negative or what? More negative. Because look, this is negative 70 because you have so many potassium ions. If potassium ions are leaving, is this more negative and this more positive, so it makes it more polar. So you remember, so this is inhibitory. It's inhibitory to the action potential. Because remember, and we'll come back to this in a minute, an action potential looks something, well actually let me draw the little bump first. An action potential, this part here is known as depolarization. In order to get an action potential, which means in order to get a thought or a feeling or a movement to happen, you have to depolarize the membrane, which means this has to become less negative, that has to become less positive. But this is becoming more negative, this is becoming more positive. So this is actually inhibiting the action potential. Does that make sense? It's making it harder for the membrane to depolarize because you're letting potassium out. I'm going to ask one more time before I move on. Does that make sense so far? Okay. So now I'm going to draw the sodium channel. There's also a sodium leaky channel. Let me get closer so it's neat because people freak out when sodium ion leaky channel. Now, in which direction is this? In which direction is this sodium going through this channel? And down into the cell. That's correct. So now sodium ions are going in that way. These are leaky. These are always on. So these don't go off. They're just holes in a membrane that only allow sodium through. The other one only allows potassium through. They're constantly on. So is this leaky channel IEP, inhibiting, or is this exciting post electrical potential? An SP. I can't believe I'm putting E. It should be SP. EPSP, or is it? Why is it EPSP?
Because it's doing the opposite of what the other one did.
That's right. It's in the opposite. That's a good way of thinking about it. Yes, that's excellent. It is. This is a leaky sodium channel. Is because it's making the answer is because it's making this side less positive. And as you enter, it's making this side less negative because you're adding positives to this side. You're taking away positives from the outside. That's making the inside and the difference between inside and outside less. So it's actually depolarizing the membrane, which is what an action potential, that's how you start it. You start an action potential by depolarizing. That's what this phase is. You allow sodium to rush in. Okay, so that's the beginning. Those are those two. There's a third important, at this point, they're kind of even, aren't they? They're even, one going in, one going out. There's more potassium ion channels. There's more potassium leaky channels. That's something that's important that you should make sure you know. There's a lot more potassium ion leaky channels than the sodium. So that means it's a lot, that's what's helping keep the membrane -70. So even though it's leaking in both directions, it's leaking more out, positives are leaking more out that are coming in. The next is a bigger protein. It's more complicated. This complicated protein is called, can you guess what it's called?
Oh, the Na plus K plus.
That's right, ATPase pump. Now this is going to take ATP and make ADP. The phosphate's going to stick on it, and what that's going to do, and you can go look at the details that I've given you in your notes. That's going to, at this point, what it's going to do is, because it's using ATP, it's going the opposite of the concentration gradient. So 3 sodiums go out. Let me draw it this way. 3 sodiums go out. That's right, and 2 potassium go in. Very good. That's right. You do. You do pay attention, just not enough. It's enough, but I don't know. I just think you could do better. So we have 3 sodiums go out and 2 potassium ions go in. Now, is that making the inside, is the sodium potassium pump, is that doing IPSP or EPSP? Is that making it?
But it's more in it, so it's EP. Or can it do both?
Well, it's taking 3 out, 3 potassium out, and 2 potassium in. Is that making the outside more positive or less positive? 3 are going out, 2 are coming in. What's the net difference? 1. You're adding 1 every time it turns. So you're adding to the outside. So it's making it more polar, right? If it's making it more polar, it's IPSP. So it's really just maintaining these two. These two are all 3 of these together are maintaining the -70 potential. Okay. All right. So now, how do we get an actual action potential occurring? Like, how do we get this to depolarize? Well, there's another set of, and I'm just going to go down a little further here. Down the membrane, and you have another protein, 2 more proteins.
That's more polar. This polarized, this depolarized.
Here you have the voltage gated sodium channel. And then here you have a voltage gated potassium channel. Okay, so this is going to let potassium out, the other is going to let sodium in. But when is it going to happen? When is it going to allow sodium in and potassium out? This is going to let sodium rush in. There's going to be a lot of these. There are a lot of these, so this is going to happen very quickly. And this is going to allow potassium out. Remembering potassium is going to repolarize and sodium is going to depolarize because sodium is rushing in, so it's going to depolarize the membrane, which is the whole beginning of the action potential. Well, when do these channels, when do they open? The key is in the word, in their name. When you change what? The voltage. Excellent. When you change the voltage. That's correct. So that implies that we have to change the voltage to get these to open. So let's go back to this chart. So depolarization happens when the sodium voltage gated channels, and this is already written in your notes that I gave you, open. When they open, the membrane depolarizes, you have the beginning of the action potential. Now the question is, what gets them to open to begin with? How do you get these, how do you get the change? We have these three proteins maintaining -70. How do we get the -70 to change more positive? How do we make the outside more negative to begin with, to get this little bump to go above what? By the way, how positive do we have to make it? If this is at -70, you can look at your notes. Say what? Yes, that's right. Well, that's how we're going to use the pressure ones. That's right. That's good. But where's the, at what point do we have to reach before you finally get, and I misdrew this. This should, yeah, no, I didn't. At which point, how high do you have to go to make this thing actually go into a full-on action potential? How positive? -55 is correct. So you have to -55 millivolts. 50 is fine. These are general numbers. It could be 50, 55, 53, 56, something like that. It could be -70, -80, something like that. You know, the average is -70. And by the way, just for future reference, up here is about +30 millivolts. So that's it. Again, you're going to go. This is the electrical potential. You're going to go from gradient -70, -55, all the way up to +30. So we have to get this to -55 to get these voltage-gated channels to open. The question is, how are we going to do that? How do we get that to get these voltage-gated channels? How do we change that membrane potential along this axon to make it to go to a -55? What channels have to be? So there's 6 of them. I gave you 6, or not 6. There's a couple that we've talked about. We have the pressure neurons, and you have the ligand-gated neurons. Ligand-gated channels, I should say. And I really shouldn't say neurons. I should say pressure channels as well. There are channels that are light sensitive in the retina of your eye, the rods and the cones. There are some that are sensitive to temperature. In all these cases, what happens when something gets too hot, or when there's too much pressure, or where there's enough ligand? Remember, ligand, I don't know why I put ligated. I don't know why I did that. Trying to say one thing and write another. Ligand-gated channels open when? If you did the ecstasy case study, you know. Neurotransmitters is correct. So this is the neurotransmitter. Opens the ligand channels. Also, there are alternatives to neurotransmitters. There are drugs like morphine. I'm probably misspelling that, but whatever. morphine, dopamine. Dopamine is a neurotransmitter, but ecstasy. What are some of the others that we talked about? Heroin. So these can all take the place of neurotransmitters, and what all a ligand is something that binds to a protein that opens a channel. That's it. It binds to a protein, opens a channel. That's all ligand means. That's all. When you see ligand means usually a protein, but it could be anything that is binding to a protein that makes something happen. So that's the ligand. Pressure channels, if you increase the pressure, so there are these channels that if you increase the pressure, it opens a channel. It's just that simple, like pushing a door open. You push your fingers, have a lot of these. You push, and you feel the push. Or something touches you, you feel that opens up channels that starts this process. Obviously with the light sensitive, I don't think I need to explain that. It's just light. These channels exist, rods and cones in your rods and cones of your retina. Temperature channels, under certain temperatures, the channels open up. If it gets too cold, other channels open up. So these proteins exist in the membrane. So this is what we call the stimulus. And these are the channels that are opened up by those stimuli. So different neurons in your cells have different versions of these stimulus-gated channels. So, okay. So if it's a ligand, it's going to be, or whatever it is, it's going to be here near the head. So they're going to open, and only if enough of them open, only if enough light, only if enough of the ligand of the neurotransmitter or the illicit drug or whatever it is, only if there's enough pressure, only if the temperature difference is enough, will you get the ions opening, enough of these ions opening to do what? To get the depolarization, the voltage gated channels to open up. So if you get if enough of these open, it gets the membrane to negative 55, then these open up. The sodium open up. As soon as the sodium open up, sodium rushes in, boom, you have a depolarization. And that depolarization depolarizes the next group, which depolarizes the next. So this is propagated. It's called propagated. You get one to the other to the other. So it just goes like dominoes, very quickly. Incredibly quickly. Is it time to go? All right. So I'll finish this tomorrow. I hope this helped. Have a great day.